Okay, so thanks everyone for joining this tutorial for the category theory. Today's speaker is Dr. Stephen Phillips from Advanced Industrial Science and Technology, ICE, in Japan. And he has been a long-term collaborator for us, Qualia Structure, and Hayato Saigo, and I have published a paper on enriched category theory on Qualia Structure this year. And today he is going to give an introduction on the category theories from basic, and this is supposed to be a, tutorial for cognitive science audience, which will happen in next week, I think, in Canada, Toronto. And here today we will have a privilege to ask questions to Steve for anything that you have you don't understand, or you have a question. So after 25 minutes on starting, we will stop for a while, 5 minutes or so, and then take any questions up until then. And I'll post a link to YouTube around them, and at that time you can also check if any part of the explanation you missed was clarified by reviewing that during the review resting time, 4 minutes. Okay, without any further ado, if no questions, please go ahead, Steve.
Okay, thanks now. Thanks for the chance for giving this tutorial. So it's going to be pretty basic, so I don't really assume much mathematical background. And we're going to cover the basics up until this concept called universal construction. I'm going to do it from two perspectives. One is a sort of geometrical perspective, and one is an algebraic perspective. And the starting point of contact between category theory and cognitive science is some notion of compositionality. So here is the sort of the outline. Today I'll do parts 1 and 2. That is an introduction and the basic concepts. And then tomorrow these basic concepts will then provide the foundation for tomorrow's talk on this notion of universal construction. And so let's just start with the sort of basic points that I hope you would get out of this talk, or this tutorial, is really three basic questions. That is the what, the why, and the how of categories. When you're introducing category theory, people who are not really familiar with the topic, probably the first question people ask is, what is category theory? And category theory can be considered from many different ways, but for the purposes of introducing this to cognitive scientists, there are two basic notions that cognitive scientists are familiar with, and hence it's natural to think of category theory. That is a notion of structure, the structure of cognition, and also the notion of analogy, as in analogical thinking. And so it's natural then to introduce category theory as a sort of a formal theory of structure, or a formal theory of analogy. But what we want to get to in this tutorial is this concept of universal construction, and hence category theory can also be thought of as a theory of universal properties that are sort of common to a whole collection of things that you're interested in. That's the what, and then the why. Why is category theory important? In particular, why should it be important to cognitive science? Why would you want to study it? Well, one way of thinking about category theory is as a kind of lingua franca for cognitive science. Now, cognitive science was originally introduced. The field of cognitive science was originally founded around the 50s and 60s as a sort of an umbrella or interdisciplinary field for other fields studying the nature of mind, for example, philosophy, psychology, neuroscience, and so on, and linguistics, and so on. So it was intended to be a sort of an interdisciplinary field, but as we've progressed, somewhat ironically, cognitive science has become more specialized rather than generalized. but that leads to the problem where we have many different models from many different groups that are highly technical, but often difficult to translate between models. And so you can think of category theory as a kind of way of doing this sort of translation. Another reason is this notion of ad hoc assumption, which prevails in science, particularly in cognitive science. And that is, science is more than just about fitting data. It's also about connecting the explanation to the rest of the scientific enterprise. And so often when we fit data, we often introduce assumptions. Its purpose is really just to account for the data, but that have no other independent motivations. And so this leads to the third point, how can we use category theory in cognitive science? And this leads to the point of the two-day tutorial, and this is the notion of universal mapping principle, that is cognition as a kind of universal construction. And so if you want to have something to read about these ideas, there's a paper in Cognitive Studies that sort of gives a brief introduction to some of these ideas that you may want to check out. So the schedule will be for today. I'll just talk about the category theory concepts I want to introduce. The basic ones that all introductions to category theory have to go through, and that is the concept of a category, the concept of a function, the concept of a natural transformation. But I want to do this by aligning these concepts to something that's more familiar to cognitive scientists, and that's some notion of compositionality, some notion of representation, of mental representation, and then some notion of computation over those mental representations, i.e. cognitive processes. And then in the second day, I'll go into the notion of various notions of universal construction. Now, the trouble with category theory is, particularly as it's presented, as it's written primarily by mathematicians and computer scientists for mathematicians and computer scientists, it's written in a very technical way, and it's often unclear how these, there is a plethora of concepts to get through. It's often unclear how these concepts are all linked together. And so what I want to do I want to present this idea more conceptually, more intuitively, by looking at this notion of this commutative square of relations as sort of the linking geometrical relationship between all these various concepts, and by doing so, give a more intuitive feel for what category theory is about. So let's go to the starting point then, the point of contact where category theory meets cognitive science. This notion of compositionality is critical, is sort of fundamental to category theory, and it's also to some extent fundamental to cognitive science. And sort of a way of thinking about this is the notion of, for example, I say the expression John loves Mary. Okay, there's a syntactic representation of that, how the words John loves Mary. And there's supposedly some correspondence between that syntactic representation and the semantic representation, semantic version of that. That is some relationship between John the person and Mary the person, a relationship between the two. And we can think of this as a kind of a square, where on the left-hand side, we might have the syntactic form of the expression, and that somehow gets mapped by this row into some sort of semantic version of this thing. And that's a sort of a basic conception of compositionality in cognitive science. And what I want to say is that this has a very straightforward connection to compositionality in category theory. We're going to use that as a sort of starting point. Now, from there, let's have a look at this is just an overview of the concepts. Now, it looks like there's a lot of concepts here, but in fact, they're all closely related to this notion of square that I just introduced. Today, we'll just talk about the basic concepts. And tomorrow, we'll talk about universal constructions. But as an overview, even within the basic concepts, there's two sort of levels. There's a sort of a within category level and a between category level. And so within a category, we need this notion of object, this notion of arrow or map between objects, and this notion of composition, sort of most primitive notion of composition, which is a way of composing arrows to make new arrows, i.e. a map between arrows. And then we have this basic relationships between categories, sort of a corresponding notion, category itself, as a sort of a collection of these objects and arrows, and then maps between categories, which are called functors, and then maps between functors are called natural transformations. Now, I said I wanted to introduce these concepts sort of geometrically. So in the brackets, we have these symbols that I've drawn in somewhat mysteriously, but they're intended to capture the idea that there's level of dimensionality. So if you think of an object as a point, then you can just think of an arrow as a link between a line between 2 points, and composition is this double line because it's a map between lines. And similarly, at the level of between categories, you can think of a category as like a dot, and a functor as a link between these 2 dots, an arrow, and then a natural transformation as a double arrow. Or, this is the crucial point here, is that the natural transformation is not just any map, it's a map such that it forms this, what's called this commutative square. And this notion of commutative square is really sort of fundamental to the conception of how all the various category theory concepts hang together. It's somewhat counterintuitive that the square itself should be fundamental, where you would think logically, think about natural transformation. You need to start with the concept of category, but if you go back into the history of category theory, for example, even Owenberg and McLean's seminal paper, they note themselves that what they're really interested in is this notion of natural transformation. And to get the notion of natural transformation, they needed the concept of functor. To get the concept of functor, they needed the concept of category. So to parallel this idea sort of geometrically, if you want to construct squares, you would need lines. If you want to construct lines, you need points. So that's the reason for the sort of inverted relationship. And then from there, once we have natural transformations, the universal construction is quite closely related. And then we have these special kinds of squares called triangles, or pointed squares. These are triangles. And so the basic point is that a lot of the different concepts really have a common genus in terms of squares. Points and lines can be regarded as trivial squares, and triangles themselves can be regarded as pointed squares. And this, I think this nicely sort of gives you the sort of conceptual intuition as to how all these concepts link together. So they're not just, when you first see these concepts, they seem quite arbitrary. You wonder why, but there is a really sort of core reason behind all this, core intuition. Okay, so really, and it's not, and the point is, it's not just any kind of square. It's what we might call a typed square. And so it's not just geometry and it's not just algebra, it's the interplay between the geometry and the algebra of these concepts that's really crucial, which makes category theory quite interesting. So this diagram here really encapsulates all 3 levels of concepts. So what I'll do is I'll just go through this step by step so you get an overview of the whole thing conceptually. So really what we want to say that natural transformation is the central concept, and that's encapsulated here by this square here. But what's going on here is the natural transformation is a relationship between these functors. You can think of a functor as a kind of mapping or an image of the original objects and arrows. So if we start here, what we see, we have this category, which you might call C. And what's happening is the functors are mapping the objects and the arrows in this category to another category, which is encapsulated here. And we'll call this category D. Okay. And so what we have is this functor F as a kind of projection of these objects and arrows. It's F here. Going from C to D. And then there's this other functor here, functor G, doing something similar, but giving a different image or a different representation of the same original objects and arrows. That's G going here. And then what the natural transformation is doing is comparing so here we have the image of F, of the original objects and arrows. And here we have the image of G, of those same objects and arrows. And the natural transformation is this mapping the image of F in G. And so now the reason why I label these, the reason why category theorists label these as dimensionality 0, 1, and 2, it may not be immediately obvious. If you see you've got a whole bunch of arrows and objects lying around, but the beauty of category theory is a bit like attention. What you tend to do is you, to make sense of the world, you tend to hide some of the information and to reveal connections between other sources of information. So if you look at the category C as a kind of point, a structured point, and you can see that we have this arrow going from here to here to D, that's the F arrow, and we have this other arrow going from C to D, and that's the G arrow, the G function. And so that's the reason why, and then we have this, what the natural transformation is really doing is a map of these arrows. And that's why it's a different kind of arrow. That's why it's given a double arrow notation from here to here. And this is also called a cell diagram. So you can see that there's kind of dimensionality here, so that treat the categories as dots, functors as lines, and therefore the natural transformations as maps between lines, and hence that's why we have this dimension of 0, 1, and 2. And what I want to do is align this with the notion of composition, representation, and re-representation or computation for purposes of doing category theory in cognitive science.
Steve?
Now, there are important points though. There's not just, so that's the sort of geometrical interpretation, but there's an algebraic interpretation as well. Typing of these, they're not just any lines and not just any squares, but they're typed in a certain way. So the arrows, for example, are arrows from an object to an object. Composition is the composition of arrows to create new arrows, see here. And then the natural transformations are not just any squares, but they're squares that have to commute in a certain way. That is, they must satisfy this expression here. And this expression just says, I'll erase all the original. Yeah. The commutativity expression just says that if I go from here across to here, so from the top left-hand corner of the square to the bottom right-hand corner of the square, well, it's the same as going from here back down to here. And this is called a commutativity condition. And it's fairly analogous to what you're familiar with in elementary algebra, elementary arithmetic, for example. The addition is commutative, means if I say x plus y, well, it's the same as y plus x. Well, you can think of this commutative square as a kind of generalized form of this notion, where if I compose the horizontal arrow with the vertical arrow, well, it's the same as composing the vertical arrow with the horizontal arrow. The exception, though, is it's generalized in the sense that these arrows are actually different. So, for example, here we have this arrow is the image of F, is the F image of F, where this arrow here is the G image of F. So just keep that in mind. But that's the reason why they call it commutativity.
Steve?
Yep.
Just a minor comment here. This is a typo, right? F of B.
Sorry, yes, you are correct. Thanks for that.
Yeah.
Very good. Yes. Okay. And so that's the basic, that's the way the three concepts sort of hang together. So once you see that, you have a sort of a conception of how, these three basic concepts are important to categories. Typically, a lot of this information is hidden, and you just see the square with the others. But I've given them both levels. Okay, so that's that. Let's go now to. Okay. Now let's go now to compositionality. Now, compositionality. I've said that there are these three levels: the levels of category, functor, and then natural transformation. And compositionality also operates at these three levels, which you can also think of the kind of dimensionality. So this diagram here is just an expanded version of the one I showed you in the previous slide, which shows you all the different kinds of, or two of the three kinds of compositions. So here on the left, here is our original category C. Here's our original category C, which contains a couple of morphisms. And these morphisms compose. So if I have an arrow or a morphism F, arrow and one G, then there must be a composition of these two, written G of F. Okay, so that's the composition. Well, let's call this let's stick with the geometrical interpretation. Let's call this vertical. Okay, and you see a corresponding version of this as a result of the application of the functor right here. And so that's the F image of that composition there. And then we have a G image of that composition. That's another functor doing the same sort of thing. And then we also have another functor, yet another functor, H, doing the same thing. So that's the vertical image. That's a within category composition. We also have horizontal, and this is the composition of natural transformations. So the beauty of all this is that functors, and we have arrows within categories. So functors are also arrows, but between categories, and then natural transformations are also arrows, but between functors. So the arrows compose, so we have this notion of composition. So we have a natural transformation going here, and another natural transformation going here. So that's a natural transformation from functor F to functor G, a natural transformation from the functor G to functor H. And therefore, we must also have a natural transformation going from F to H, which is a combination of those two. And so we can think of this as horizontal composition. And then finally, there's a third version, the composition of functors, which is not shown here, but you can see that there is a functor going in this direction, so this out of plane direction. And if I was to extend this diagram, I could have a functor applied to F, but it's not shown, but it would look like another arrow here, and then you'd have a composition as well. And these compositions also interact, so you can also have compositions of functors with natural transformations. But that's the basic perspective. Okay. Now, the next two slides, and this finishes up the introduction of today's talk, the first half of today's talk, I'll look ahead at this notion of universal construction from this same geometrical perspective. Now, notice in the previous slide, we had a functor here mapping A and B. Now, in this slide, we have a special case of this situation where both A and B map to the same object, X. Okay. And in that case, what happens is that A maps to X. This is called a constant functor, by an analogy to a constant function, where all the objects get mapped to the same object here, in this case X. And all the arrows get mapped to the same arrow, is labeled 1 up, 1X. And this is a special arrow called an identity arrow. Okay. And so your square would look like this, with X on the top left and the bottom left corners linked by this identity arrow. And then we have this, our normal G functor on the other side, G image on the other side. Now, in this situation, we can simplify this square to a triangle by noting that, and the reason for that is because every object is associated with an identity arrow. So if you see a diagram looking like this, well, it's assumed that you understand that there is this, it's assumed that you understand that associated with this object X is a loop, an arrow that goes back on itself. From there to there, labeled 1, usually labeled 1, and subscripted by the object that it's attached to. This is called the identity arrow. And so, and it's for this reason that we can regard the triangles as special squares, where this triangle actually can be expanded into squares. So that's the conceptual link between the two. Now, once we've done that, then we're very close to this notion of universal mapping property, which is the foundation for this notion of universal construction. And so in category theory diagrams, all these objects have loops. But because it's a basic rule, a basic law of categories, that all objects are associated with a loop, they're usually omitted from such diagrams. It's unnecessary, it's redundant. That's why that's the connection between squares and triangles, which we'll use in tomorrow's talk when we introduce the notion of universal construction. And then finally,
Steve?
Yep.
So maybe I think some people, including myself, are not probably clear why this is called universal, or what's the sort of significance of this to the cognitive science, if you can elaborate on that.
Okay. I was going to leave that till later.
Okay.
Because this is a look ahead, a preview. But the reason why it's called universal is that and which I'll explain in more detail tomorrow, is that all the arrows here factor through this arrow here called the mediating arrow. The F, put briefly, it's called universal. Every F here in your category, put very briefly, every F is constructed or composed of this common arrow here, this phi, and this unique arrow here, G of U. Now, the exact details, it'll take me a little while to explain. And all I wanted to show here is that if you look at the definition of universal morphism or universal mapping property, it seems to come out of nowhere, but in fact, it's quite closely related to the notion of natural transformation that we're introducing. And all I want to do here is just show that these two things are quite closely linked at this point.
Okay.
Does that help?
Yeah, I think for me it's okay.
Okay. I'll explain more about this tomorrow. The general point I want to make is, in fact, despite their dissimilar appearances, they're actually quite closely connected, these concepts. And then finally, for the last slide before we go to the break, is that, so that slide and this slide are relating to this notion of universal construction. Often what we want to do, we don't just want to know the structural relationships between things, we also want to do computation over this. And there are two basic ways of doing that. There are many basic ways of doing that. One of the ways is the notion of recursion, how recursion fits into the picture. Again, if you look at the definition, it seems to be a bit unclear how it's motivated, but in fact, it also comes back to this notion of a commutative square. And it's a special case of the commutative square where one of these edges, in fact, it's the top edge here, is an isomorphism. Okay. So previously, I just showed you a situation where there was an arrow from here, on the top left-hand side. Previously, I showed you that the squares had arrows always going from this top left-hand corner to the bottom right-hand corner. General form. But in special cases, this arrow here is an isomorphism. What that means is that there is also an arrow that goes in the other direction. Inverse. So in this special situation, what that allows us to do is instead of, previously I showed you that there are two ways of traversing the square. The clockwise, going from the top, along the top of the square down to the bottom of the square, that's clockwise traversal, and an anti-clockwise traversal going in the other direction. But if this edge here is actually an isomorphism, which means that there is also an inverse arrow, it also means that we can go, there are also two other ways of traversing the square, from here to here, F. And we can use the isomorphism, the inverse, to go in this direction. And the point is, these two things are equal. Another property. Now, what that allows us to do is recursion, and this the bottom diagram explains this point. Normally, what you want to do in a recursive scenario is to compute a map from, say, A to B. So your goal is to go from A to B. But often, you can't do that directly. You don't have enough information. Or the A is actually some sort of complex object. So if this arrow is an isomorphism, what you can do is go back this way, split up the A into parts, and then go down and across. Now, if you do that, you may still have the problem that the A is still too complex to be able to go directly. You still may not be able to go down here. But what recursion allows you to do is you can do the same thing. You're splitting it up into this one. At this stage, I won't explain what that exactly means, but you can see that we want to go from A to B. We can't do that directly, so we do it indirectly by decomposing A into its components. But in the recursive scenario, we also often get A again in some form. So we can just do the same thing again. Apply the decomposition go this way. And we can keep going until we terminate, until we've got completely decomposed the object to what's called a terminating condition. And that's this condition here, which allows us to make the jump. And once we do that, then we can go back in the original direction. And then originally, and this is sort of the geometrical perspective of recursion. So what we originally want to do is compute this rightmost arrow. We can't do it directly, so we have to do it indirectly by decomposing A along this line here, because we have this isomorphism, this invertible arrow, until we get to this terminating condition right at the end, far left hand end. Once we hit the terminating condition, then we can go bridge this gap and then come back. And that's the sort of basis of recursion. And the point I want to make here is that this is a look at it for tomorrow, is that this also follows the square, but it's a chaining of these squares that allows us to do it. So,
okay.
That is
yeah, perfect for the 25 minutes.
Yeah. And so probably you want to have a break.
Yeah.
I think.
All right. Thank you.
Can you go back to one slide? Yep. I think I found the error in the slide. Yes, regarding the recursion in dual factors, you show that f and psi 0, phi 0, blah, 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 phi n.
Mm-hmm.
And n plus f plus phi. But I think it should not be phi, right? It's instead psi, no? Because
there's a
okay.
Yeah, well done. Yeah.
Okay, good.
I've changed my symbols from phi to psi for some reason. But yeah, that's right. You're
okay, good.
So this side is psi.
No, they're all phi or psi. Sorry, I'm sorry. Yeah. One.
This is phi, right?
Yeah.
A to A is phi, according to this one.
I've confused the situation because let me fix the slide, but actually this is a special arrow. This is a general situation. Sorry, this isomorphism is a special case. Okay.
Maybe you can fix it later.
Yeah. Actually, the reason is because this is a sort of general scenario, but in this particular case, it's a special kind of error in this scenario. And so if you were to translate from this square to this square, this should be phi, and this should be psi, and this should be, it is actually correct the way it is, but these arrows are actually special arrows and not just general arrows. So, sorry. They're actually called initial arrows in this category situation. So, sorry.
Okay, so shall we take a break? Or is there any further questions at this point? If not, then let's take a break. Steve, can you release the screen sharing so that I can, I'll put up the timer for the break. Okay, so let's restart. But by the way, Steve, sort of general question about the recursion. So the scheme that you showed at the end of the first part, do you think that's relevant for something like self consciousness, self awareness, as well as recursive kind of thoughts or recursive generation of the language and things like that?
Yeah, in a sense, yes. So you can think of the. Can you see my screen?
Now you can
maybe
share it. I released the screen sharing.
Can you see me?
Did you share the screen?
Okay, sorry.
I think you still haven't
Yeah,
shared the screen.
I think yes. The idea is that. Well,
Yes, okay, now that's fine. Now it's fine. Yeah.
in a sense, yes. You can think of the base arrow as a kind of base, and then you're looking to manipulate the space in some sense. So there is this two-way connection between this level. So did I But in recursion generally, this can be quite deep, where you might expect the ability to look at one's internal states to be quite limited, one or two levels, but not n levels.
Okay. Are there any questions so far from the audience? I'm checking the YouTube, but there is no question from YouTube. So here, if no, nothing, then let's move on.
Okay. So just to recap, we have this basic notion of category functor and natural transformation, this sort of hierarchy of concepts. But what we want to do now is that's a sort of geometrical view. What we want to do now is to move on to this relationship between these three concepts and how we might use them in cognitive science. And the first one is the relationship between categories as a way of doing compositionality. So at a basic level, you might think that composition is just a method. Compositionality is just a basic method, as a method for putting two things together to form something else. And so there are many possible ways of doing this. And the classical notion of compositionality in cognitive science is the classical version, is where you have some symbol for each of its parts, and you put the symbols together to build up, to represent some sort of complex situation. That is, the composite symbol is built up from constituent symbols and their relationship. For example, the concept of red circle is built up from a concept of red and a concept of circle put together in some order, where the order is important. So, for example, red circle, not to be interpreted as the same thing as circle red. The motivation for doing this in cognitive science, one of the motivations is to address the so-called systematicity and productivity properties of cognition. I'll talk more about this later. But basically, the idea is that our ability to construct representations are not just arbitrary, but it's organized around sort of clusters of abilities. So, for example, if you can think about red circle, and if you have the ability to think about things like red, blue, and green, and things like circle, triangle, and square, then you can do all combinations of that. And some sort of compositional principle of compositionality affords this sort of clustering of abilities. Now, in category theory, the basic notion of composition is the composition operation, which I've already introduced. It's a composite arrow built up from arrows in composition operation. It's sort of a circle symbol here. So, for example, G of F is built from arrows F and G applied to the composition operation. And just like in cognitive science, the order is important. So G of F is not the same as, in general, it's not the same as F and G. And of course, the motivation is analogous. Complex structure as a combination of arrows. So here we move more into the algebraic view of categories. And a definition of, there are a variety of definitions for equivalent definitions of category. And usually they involve some notion, they introduce it, as I've already done, introduce objects. A category is a collection of objects and a collection of arrows and some sort of operation for composing arrows. Now, the way I've done it here, though, is to introduce it as a six-tuple, where C0 is your collection of objects, usually labeled A, B, and C. C1 is your collection of arrows, and the composition operation right at the end. And there's three extra bits in here, which I'll discuss in a minute. But let's just focus on the three basic. So at this, when you see a definition of category, it's very abstract. It doesn't tell you, doesn't say what the A's and B's are or what the F's and G's are and so forth. So that's just the basic definition. There's a couple of rules for how these things relate, but that's it. And so you're often left with no intuition as to what's going on. But one way of thinking about categories as a generalization of sets and functions. So if you need some sort of concrete handle on what's going on here, you can think of, for example, the A's and B's as sets, F's and G's as functions between sets. And the composition is just a way of composing functions to get new functions. Now, in addition to that, there are some important aspects. It's not just any collection of objects and arrows. One thing, each object must have an identity arrow associated. So, for example, if you're talking about the arrows are functions, then that would be just the identity function. And each arrow must have is always from an object, called its domain, to an object. Okay. And when you compose arrows, you can only compose what's called compatible arrows, as this diagram shows down the bottom. What I want to do here is algebra. The reason for doing this is it ultimately makes the transition into when we go to look at functors, a bit more straightforward. So an arrow will be usually written, an arrow F will be written like this, as it's always directed from an object A to an object B. A is called the domain of the arrow, and B is called the codomain, very by analogy to functions. So A is the domain of a function, and B is the codomain of the function. And now, so that's and you notice that they're indexed by 0 and 1. Again, it gets back to the dimensionality aspect. So the objects are zero-dimensional things. So that's why it's C subscript 0. And the arrows are one-dimensional. So it's like C subscript 1. And it's analogous to the way you'd introduce graphs. So, for example, when you talk about a directed graph, you talk about it as having a collection of vertices, where you can think of the vertices as analogous to objects, and a collection of edges, and the edges is analogous to arrows. And then each edge has a source and a domain, which is analogous to domain and codomain of an arrow. And so on. But however, graphs in general are not categories. They're missing two important things. They're missing the identity and composition. Now, the way I've done it here is to make, usually they would just say this verbally, but what I've done here is to make this more explicit by introducing the domain and codomain function. So what that is the domain function just takes an arrow and just tells you what the domain object is for that arrow. It's just a map from arrows to objects. Likewise, the codomain function just tells you what the codomain is for each function, for each arrow. Okay. And then normally they would in the definition, would just assert that every object has to have an identity arrow. And you can do this assertion also as a function by linking a function called ID for identity, which just takes each object and returns this identity arrow, which looks like this. Okay. Identity arrows are special, like loops, and the domain and the codomain are the same object. Okay, so that's the reason for having these extra terms in here. So we have objects, collection of objects, collection of arrows, and composition operation. And we also have these three other functions, just give you the relationship between the objects and the arrows. And in addition to that, the composition has to satisfy two properties. And again, we can do this by analogy to what you're familiar with. One is called the identity property. So if you compose any arrow F with an identity, well, it's the same as the original arrow. So compare that with the situation in elementary multiplication. If I multiply any number x with number 1, then I just get x. So that's the analogy there. It's called the identity condition for composition. And similarly, the composition operation must also be associative. And what that means is that the order of the operations is not important. So, for example, if I compose G and F first, then followed by H, it's the same as composing H and G first, then followed by F. And again, this is analogous to multiplication. In addition, they're both associative operations. Again, if I multiply Y times Z and then by X, it's the same as multiplying X by Y. That's the reason for that. Now, and if your collection of objects and arrows satisfies all these conditions, then you have a category. Now, getting back to this point about, it seems like the identities actually don't do very much, but in actual fact, they are important to category theory as is the composition operation, for reasons that will become clearer later. But one thing to note here, getting back to the geometric interpretation, is that if you have an arrow from A to B and an arrow from B to F, B to C, then by the rules of categories, if it's a category, then you must also have this arrow from A to C. You have this triangle of arrows. This double arrow here just indicates it's the compositional relationship between F and G and its composition. Now, this triangle relationship is also equivalently expressed as a square. So again, we get back to this notion of square as sort of a linking concept, where the arrow, the left-hand edge is just the identity. This is what I showed you a few slides ago. But again, because the axioms of a category, the rules for having a category insist that every object must have an arrow. Normally, we don't display these identity arrows. So that's the algebraic definition. Now finally, we get to some examples of categories. So briefly, I said that before that if you need a concrete example of a category, you just think about sets of functions. But be aware, though, that the definition of a category is quite general, and that these object scenarios that need not be sets and they need not be functions. A very simple example of this is an ordered set, where in this situation, for example, say you have a statement that Anne is shorter than, that is not taller than Ben, and then Ben is shorter than Kaz, then by the transitivity property of order relations, then you also know that Anne is also shorter than Kaz. Well, this arrangement here is just a category where the order relationship, shorter, is an arrow between Anne and Ben, and also there's an order relationship between Ben and Kaz, and therefore by transitivity you also have this order relationship. Yes. And the point of this slide is just to show you that categories are quite general. The objects here are just these elements of this particular set, Anne, Ben, and Kaz, and the arrows in this case are just these order relationships. And the identity relationship is because the identity arrow comes about because Anne is not taller than Anne. It's less than or equal to the relationship here. And formally, an ordered set, which is expressed as a set P with this order relationship over, corresponds to a category where the objects are the elements of the set P. The arrows are these order relationships, and the identities are the reflexive relationships. And then you can go through and step by step and see exactly how this corresponds to the definition I just gave before. A very simple example of this, of course, is the natural numbers. Natural numbers, together with the usual order relationship, constitute a category.
Steve, can I ask a question here, please?
Yep. Oh, hi, Rick. How are you?
No, not bad. How are you? Sorry, I was on Facebook before, so I couldn't interact. I just finally worked out how to come in via the Zoom. If we could go back to the previous slide, please.
Yep.
So we've got the domain codomain maps. So DOM is a function. So the arrow F in that case has domain A, and the arrow F has the domain B, codomain B. So that's basically saying that F is the specific arrow between object A and object B. And yet when we come to the next slide, you're using shorter as a label on arrows, which seems to be implying that it's the same arrow shorter between Anne and Ben as is the arrow shorter between Ben and Kaz, but that seems to be inconsistent with the previous definition.
Very good point, and I like that.
Could I just also make a related point? I've made a number of attempts to try to get into category theory, and I've always sort of stumbled almost immediately on the semantics of these diagrams. It's not clear to me whether the object in the category theoretic point is a specific object or whether it represents some class of objects, in which case it sort of implies the existence of a quantifier. So I've never managed to get past the diagram. So what the hell does this mean?
It's a very good point. And down here, what I've done is subscripted to address that very point.
Yeah.
It's generally category theorists expect you to make these transitions automatically.
Yeah, I figured that there was something which was very obvious to the people who do it, which was completely sailing past me.
Yes. So that's why what I've done here is to index these less than or equal relationships with their actual objects. So this one here, for example, is shorter than, in fact, should be subscripted with B, C, or the object. So they are, in fact, different arrows.
Yeah, so the fact that you put the label shorter on them is basically you're saying, there's a whole set of these arrows, which in some sense mean the same thing, and this just happens to be the instance of those arrows which goes between Ben and Kaz.
Yeah, exactly. And another way to look at this is from a relational database perspective, and they would do this somewhat similar, and that is you would have a table here of rows, and then you would have your N would be here, and sorry, hard to draw this, and B and Ben would be here as one. So the relationship. So the whole table is shorter, but that's the particular instance.
Okay, and each row is then each row is an individual morphism.
That's right.
Yeah. If it just pop back to the previous slide again, if you'll indulge me for another 30 seconds. So I know that if I'm to the extent that I get this, given that you've said that really category theory is intensely general, and so presumably when you give these axioms that something must obey to be a category, then the mathematicians really take that seriously. Whatever it is, doesn't matter what it is, as long as it obeys these conditions, it is a category from the category theory point of view. Yeah. Once again, we're getting back to this example of sets and functions as being something of an intuition pump. It seems to me that from the category theoretic point of view, yes, these might be sets, and sets have internal structure, but from the category theory point of view, the category theory doesn't see the internal structure of the objects. It just knows the objects as black box individuals. Ditto the arrows. It seems to me from the category, from the category theory point of view, it sees them as black boxes. Sorry,
that's a good issue to raise. But the category theory does respect that.
That's the point I was going to get to. So essentially what you're saying is, although category theory doesn't see what's going inside the boxes, which are the objects, and the boxes, which are the arrows, by these other conditions that it must respect in order to be a category, what you're saying is magically, this means that it does behave as though it's respecting the structure thereof, even though it doesn't actually look into it from its own point of view.
Yeah, there's a nice subtle point that you're raising there, and I'm going to come to that as time. But the short answer is that it's getting back to what I briefly said probably before you tuned in, was that you can think of the category theory as a bit like a tension. So these levels. You're focusing on at some level and hiding the other internal information. You can bring that information back when you want to. Okay. It's a nice point, and I'll try and bring it out in the subsequent slides. As I move along.
Okay, I'll get out of your head. Sorry.
No, it was good. It's a good point. So this example illustrates a very simple. Special kind of category where there is at most only one arrow between any two objects. Now, the next example also exercises another aspect of categories, and that is the composition aspect. Now, here, this category has only one object, but it has multiple arrows between objects. So think of natural numbers and addition. It's a very simple example of a category called a monoid. For example, 1 + 2 = 3 is a kind of composition that cognitive scientists would normally think of this as composition, but we'll get to that later. What's happening here is that the arrows themselves, in this situation, we only have this one nondescript object, which I've labeled star, and I've just repeated it here to expand the viewpoint. And each arrow here is a number. So here's the number 1 corresponds to this arrow, the number 2 corresponds to this arrow. Now what's happening here is that the composition now is actually corresponds to the addition operation. So when you compose the arrow 2 with the arrow 1, you get the arrow 3. And the identity in this case is just 0. Because, as you know, 0 plus x equals x. And so this corresponds to the condition for what happens with the identity condition on composition. And so here we have another kind of object, another kind of category, which has just one nondescript object. All the arrows are loops corresponding to the numbers, but the composition itself is the addition. And it's associated because addition is associated and it's unital because addition.
Steve?
Yep.
It's probably related to what Ross also kind of mentioned. This object in this case, you call it as one object, but it feels probably weird to beginners when you talk about this thing as one thing. The bottom one is okay, but here, because you are connecting these two things with one.
Okay.
But it looks like it's the same thing.
Yep.
Can you sort of
so let me redraw it.
Provide a bit of the explanation?
So we can draw it another way. The object is here, and then all the arrows are in fact loops, but they're not identity loop. They're not identity arrows except for one. So here's the number 1. And then there's another loop. With the number 2. And so on and so on. And there's also, the 0 is also the identity arrow, which is also a loop. And the trick is how to combine these arrows. And that's where I've just rewritten it this way to see how they combine. And it is the composition operation here. So what you would say is you'd say 2, the arrow 2 composed with that composed symbol, the arrow 1 corresponds or is equivalent to saying 1 plus 2. So the composition operation here just corresponds to addition.
I see. So maybe just to make sure. So here, in this case, what do you mean by this object star corresponds to a bunch of numbers, and you don't care about the identity of the numbers as long as it's one of the natural numbers?
No. The object here, let's just call it A, for example, not star. Let's just call it a specific object A. But it has no role other than it's the domain and the codomain of every arrow. So the tricky thing about this one is that the numbers are actually arrows, but the object doesn't have, there's only one object. It doesn't have any particular role other than it just serves to be the domain and the codomain of every arrow. And this is a bit of a natural leap because we're normally familiar with arrows as maps or functions. But here, we've actually given them the role of an individual number. It's a bit of a conceptual leap that you need to make to see this particular example. So if it's a bit too much of a leap, we can move on. It's not really crucial.
Actually, Steve, I mean, I presume it would be wrong to think of that A as being equivalent to a data structure with state that gets updated. I mean, because what you're saying is it's just the domain and the codomain, so it doesn't really have anything which changes.
No, it doesn't.
So that would be a wrong view. But I seem to recall once hearing somebody say that it's effectively in category theory, everything you know is actually captured in the arrows. So if that's the case, then essentially, you've only got the A here because the arrows have to start and begin somewhere, but all the information's actually in the arrows.
Mm-hmm. That's right.
Would that be reasonable?
Yep.
Yeah, okay.
Okay, so we should just think this star as a kind of a placeholder.
Yeah.
Okay.
There's only one thing, and it doesn't do anything other than serve to be the start and end point of every arrow. Okay. Here's a more familiar example of category sets and functions. And this is a useful one because a lot of the notation comes from sets and functions. The reason we use, for example, F as a stand in for a morphism is because you often treat the morphisms are often functions of some kind. So in this case, now this gets back to, actually this slide also addresses Ross's earlier question. So let's just go through this. Here in the category, the sort of prototypical category set, the objects are sets. So they have some internal structure, i.e. the elements that make up the set. The arrows are functions between sets, or total functions. The identities are identity functions, i.e. the function that maps each element back to itself. Domain and codomain is the same as before, and so on and so forth. And composition is composition of functions. So another thing to point out, you often may wonder why there's a sort of backwards reading of composition. Why is it when you compose F with G, it's not written F of G rather than G of F? But it really comes from this notion of function composition. So if you say, you apply the function F to A and then you apply the function G to the result of that, you'd write it this way. So it's G of F of A. And so this particular order, it is sort of mirrored in this composition. It's not the only, sometimes you see it written the other way, and when it is done that way, it's usually flagged as such. For example, in computer science, you'd often write it the other way because you often tend to write statements sort of in sequential order, and so it's natural to write it the other way. But anyway, this is the typical way they do it in maths. So the point here, and getting back to Ross's earlier point, is that objects and arrows, unlike the first two examples of ordered sets, where the elements were just, where the objects were just elements, no internal in structure, and the arrows were just numbers with no particular internal structure. In this case, the objects and arrows have internal structure. That is, the internal structure of an object is the elements of the set that it makes up, and the internal structure of the arrows is the actions of the function on the elements. And for this reason, we use a different notation for the arrows. It's sort of what's called a maps to arrow, which just tells you what the actual action is of this function F on the element A, send it to F. Now, here we get to the point. The beauty of category theory is we can treat things at different levels. There's not necessarily a sort of a fundamental level, but once you set your level set your baseline point of interest, then we can fix the relationship between levels. So, for example, we can treat a set as a category in its own right versus a set as a category of sets. So in the first case, where a set is a category, then the objects of this category S are just the elements of the set S. And the only arrows are the identity arrows. There are no other arrows between the elements. Okay, and that is also a category called a discrete category. Okay. But we could also talk about the category of sets when the objects themselves are sets and the arrows are therefore functions. And so we have these two kinds of notation here. We have the arrow between the objects. This is sort of the external view. We also have these maps to arrows, which tell you what the actions are on the elements within an object. And that's the reason for the two different kinds of notation, i.e. the arrow versus its action. Now, in some cases, this is quite common. For example, you can talk, as we'll see in the next few slides, we can talk about the monoid. In the previous example, we saw the natural numbers together with addition and zero as a simple algebraic structure called a monoid. Now, monoid in its own right is a category, or it can be an object in a larger category of monoids. So we have these two different levels, and we can move between these two different levels. And so to get back to Ross's point, if we're looking at it really depends on your point of view, and your question of interest, as to what you're focusing on. This is a bit like attention. What level of detail are you really interested in? If you're interested only in the relationships between the models, then the category is the category of monoids, and the monoids are objects. But if you're interested in a particular monoid, then that particular object can be a category in its own right. And that's why we fit between these levels. And category theory makes this distinction very precise, and it's one of the attractive points of category theory itself.
All right. So can we take another break? And if there is any pressing question right now, we can take it. Or you can post a question on chat, or during the break, you can think about it. So if not, then we'll come back in 4 minutes. Steve, can you release the screen sharing again?
Okay.
Okay, Steve, please. and this will be the last stretch of this today's tutorial. So does anybody have any questions so far? If not, please go ahead, Steve.
Okay. Okay, so now we get to this point about the different levels of analysis, where for example, the category, a monoid as a category versus a category of monoids. And now what I want to do is show you that how to sort of a prelude to how to move from categories to functors. So you said a monoid is a set with some binary operation and some what's called a unit element. For example, natural numbers, addition, and zero. Well, you can recast that as by saying a monoid is a set plus two functions. So, and one function is called this binary function called multiplication, which is just an operation that takes two elements from a set and then produces another element. And the other one, instead of treating the element as the unit as a special element, we can treat it as a function, as what's called a nullary function, just picks out the unit. So, for example, in the case of down here, in the case of the natural numbers, the monoid would be the set of natural numbers. This multiplication, in this case, it's called multiplication, but it's in a general sense. For example, in this case, it's just elementary addition. And the unit in this case is an arrow that picks out zero. Now, the reason for doing this is that what it allows us to do is express the monoid not as a set of elements plus an operation, but as a bunch of arrows. Specifically, the multiplication now, that is the binary operation for the monoid, is just this arrow from this the product of the set with itself to that step. And the unit element, like zero, for example, is also an arrow. It goes from this special object called one into the set. In this case, it'll be picking up zero. Okay. Now, once you do that, then you can combine these into a single arrow, where now the object on the left-hand side is really just the sum of these two objects. Now, this will look a bit mysterious at first, but this multiplication and addition, and it's intended to be in a general sense. Think of addition here as a kind of an alternative. So either you're doing multiplication of two elements, or you're picking out the unit element. And that's what this sum of these two functions are doing. And so what the objective here is to convert the definition of a monoid into a single arrow, this arrow here, as a kind of structure. This arrow captures the structure of a monoid. Now, there are some additional conditions. Of course, it's not just any pair of arrows. They have to satisfy the associativity and unity conditions that I mentioned earlier. And this also can be expressed as commutative diagrams, but I think I'll skip this point, this stage. Now, a monoid, as I said before, can be thought of as a special kind of category with a single object and a bunch of arrows. Now, a category, therefore, can be thought of as a generalized monoid where they have more than one object. And you can do the same sort of thing as I did in the previous slide. You can treat a category as a particular kind of structure, as a bunch of arrows. I think I won't go through all the details here because I think I'll run out of time, but it's the same sort of idea. So the composition operation is itself an arrow between a bunch of objects and arrows, between pairs of arrows, two arrows. The identities are just the maps that associate each object to the identity arrow and so on and so forth. And once you've done this diagram, then you can combine all these arrows into a single arrow. And so what you have down here is a category expressed as a single structured arrow. And that's the category structure as an arrow. Okay. That's all a prelude. Now, this is all a prelude to leading up to functors, why you get the definition of functor the way it is. Now, you can also talk about a category of arrows. Previously, I've just talked about objects.
Maybe Steve, just a quick question about the last slide.
Yep.
So,
previous slide.
Yeah, so this one, the point of this is that we can use one arrow to represent something very complicated, like a structure of a category in a simple way.
Yes, that's right.
Okay.
And the reason for doing this is alluded to in this slide. So previously I talked about objects as either elements or sets of elements and so on and so forth. But the arrows themselves can be the objects of a larger category, what's called a category of arrows. So here we're the objects are the arrows, alpha from A to A dash. And the arrows are now the maps of these arrows. So for this reason, it's handy to talk about morphisms and arrows, although they're used synonymously. So you might say the objects are morphisms and the arrows are maps between morphisms or something like that. But anyhow, so for example, I draw this thing here is now an object in this new category, and this thing here is an object in this new category, and the arrow is really this arrow between here. And this also gets back to Ross's point. So what we're doing here, category theory, is sort of hiding some of this internal detail temporarily. It's a bit like the psychological notion of chunking, where you sort of chunk some concept temporarily, free up working memory and so forth. And so at this level, with this level of category of arrows, we're just looking at this object, which is itself an arrow, has some internal structure, and so forth. And so if you look at the entire thing, what makes this useful is that this single arrow is actually a pair of arrows. In a sense, it's a square that preserves the arrow structure. In other words, it's a pair of arrows, F and F dash, which is a mapping of the domain, map between the domains of the two arrows and the map between the codomain of the two arrows, such that the two things commute. Okay, so it gets back to this common notion of commuting square. So going from here to here is the same as going from here to here, equal. So these two parts are equal. So it's not just any linking, it's not just any square. It has to be this commutative square. And so we have objects are now arrows. The arrows are now squares, and composition is now pasting of squares. So you paste along the common edge. This is the common edge here that's pasted. So if you have this square here, there's now an arrow. Here's one arrow, and we have another arrow. Then when you paste them together, you get another square of arrows. That's this square here. Here, to here, to here, and back to here is another square. It's called pasting squares. So this is also a category. The same principles apply. Now, the reason for doing that is a lead up to categories as structures of objects. Let's go back to the monoid case. We said that previously that a monoid can be expressed as a single arrow. Okay, so here's our single monoid as this structure, this arrow. Now, from the previous slide, we can convert arrows into objects. So now, our first monoid is this object here, expressed as an arrow. Our second monoid is this object here, expressed as an arrow. This is expressed as an object now. And so a monoid homomorphism is simply an arrow in this category of arrows, in this particular category of arrows. And we saw that these arrows are just these commuting squares. So for this thing, a monoid homomorphism is simply this commuting square between these two monoids now treated as objects. Okay. So compare this arrangement here with the usual algebraic definition of a monoid, which is given in this section here. So a monoid homomorphism is just a function from M to N, such that it preserves the binary operation, that is, the A of B, or H, the function H, the monoid homomorphism, applied to the composition of A and B, is equal to the function h applied to the individual components and then compose. And that's the condition on the binary operation. And then there's also a condition on the unit elements, they must also agree. So the application of h on the element unit for the first monoid, second monoid. Now all this is expressed in this commutative square. And once you see that, you're very close to the definition of a functor. Because as we introduced before, a monoid in itself is also a special case of a category. So you can think of this also as a particular kind of category. And this other one is also a category. Every monoid is a category, as one object category. So for this monoid homomorphism, as a map between monoids is also a functor between monoids treated as categories. Okay, so now we have a very simple case of a functor, a miniature functor, as a map between one object categories. And so that sets us up now for the definition of a functor. Okay. So we talked about categories and composition. Now we talk about functors and representations, or compositional representations. So some preliminary links to cognitive science. So representations are a basic understanding of representations, one thing that's standing in for another. The classical version in cognitive science is semantic relations between paths are mirrored by the syntactic relations between corresponding symbols as a kind of partial algebra homomorphism. For example, left off corresponds to the order of circle, square. So, there is some one-to-one. There is a correspondence between the syntactic relationships and the semantic relationships. And the motivation for this, one of the motivations for this kind of principle is systematicity of representation, as I mentioned before. Now, a corresponding category theory version is a functor as a structure preserving map or a category homomorphism. And notice the analogy here between monoid homomorphism that I've already introduced and the functor homomorphism is very similar. But instead of operating on elements, the functor operates on morphisms. And instead of the composition being the binary operation, it's the composition operation. And you can see the idea is that the functor applied to the composition is equal to the composition of the functor applied to the individual components. That's the basis of the category. That's the basis of a homomorphism, and it's the basis for a functor as a category homomorphism. Okay. And there's the corresponding idea. Composite arrow G of F is represented by the functor applied to G of F. And the motivation represent objects A and arrows F of A. Sorry, arrows F in one domain as the objects and the arrows in another domain via the functor as a representation. So we can move now to the definition of a functor. Now the definition would be sort of an algebraic style definition. It would be expressed something like this: a functor is a map from a category C to a category D. It's a structure preserving map sending objects and arrows to objects and arrows in C to objects and arrows in D that preserves domains and codomains, the identities and composition. So in diagram form, it would just look like something like this. So here on the on the left-hand side, we have our category C. On the right-hand side, we have our category D. And again, the functor is just a map from here to here. Now notice that there are two kinds of arrows I'm using. These solid arrows are the arrows within the category, and these dotted arrows are actually the actions of the functor on the individual objects and morphisms in the category. Now, in this case, I don't show the action on the objects, but you can see there's a corresponding action on the morphism. So there's several ways of introducing the notion of a functor. That's one way, where it's implied that there's something happening to the objects and something happening to the arrows in a sort of structurally coherent way. And then, but we can do it another way, and that is by using the, going back to this notion of a structure as a kind of arrow. So from this view, we say a functor is a pair of maps, F0 and F1. And of course, the indexes, of course, are analogs. So recall that zeros stands for points. So this is the collection of points, and this is the collection of arrows. Well, then you have the corresponding two maps, F0, which is the map of the objects, and F1 is the map of the morphisms. And it's not just any map; they have to preserve the structure. And what that means, of course, is because we can represent the structure as arrows, it's just a map of arrows. So F1, so what we have now is the domain and the codomain as maps, sort of in C, being sent to domain and codomain maps in D in this sort of structurally coherent way, and that's what the F1 is doing. And this is the motivation. If you recall from the very early slide, I said that the category is this sextuple of components, i.e. the C0, C1, the composition, but also the domain and the codomain, and also the identity, all expressed as arrows. You can see the reason for doing that now is that by expressing all the components of a category as arrows, then the map between categories is straightforwardly just a map of these arrows. And once you do that, then you can, so it has three components. It preserves the domains, codomains, it preserves the identities, and it preserves the compositions. And we saw previously that you can combine all these arrows into a single arrow. Okay, the whole structure of a category is expressed now as a single arrow. That rewritten like this as an object now. And so the functor now, so here we have our category C expressed as a single arrow, and our category D expressed as another arrow. And then functor F is just this map between these two objects. Again, this is another illustration of Ross's point. You can hide a lot of this information temporarily. See the high level view. Now, compare this, and what we have here now is just our general definition of a functor. Compare this with the algebraic definition expressed here. And this is an analog of what we saw previously with the relationship between monoid and monoid homomorphism, and as a simple case of a category and a functor. So again, getting back to this geometrical interpretation, we see the reemergence of this commutative square appearing here. Now, it's not just, and as I tried to emphasize at the beginning in the introduction, it's not just any square. They are typed squares. So the typing is important, of course. And so it's not just any map between here, it's this composition of maps. Okay. Called the product, and this is called the coproduct or sum. Now, because we're working with sets, the sum here is actually just what's called disjoint union, acts like an alternative. So either you're doing this, or you're doing this, or you're doing this. And the product here is the Cartesian product. It's the map of the pairs of the elements. And so there we have the definition of functor. And so the motivation for all this is that, if you look at the algebraic definition, it seems somewhat arbitrary. But in fact, if you look at the geometric form of it, it's all very straightforward extension of this idea of mapping of arrows, or this preservation of structure as this commutative square. It's a common theme that runs through all of what we've talked about so far. Okay, that's functor. And again, to emphasize this point, you can think of this process as a kind of chunking, or in this particular case, a kind of objectification, where we've taken, on the one hand, we're taking something that's explicitly given as an arrow, and sort of objectified it and converted it into an object. to look at other kinds of relationships between. In language, you might call this the relationship, treating a verb as a noun, treating an action as a state, treating a line as a point, squares, lines, and so forth. So this is transition between one level of structure and another level of structure. And this is a recurring theme throughout category. Okay, so the final basic concept that we want to introduce today is the concept of natural transformation and how it corresponds to the notion of re-representation and computation. Okay, so basic idea, transformations of representation. So the classical notion of this in cognitive science is a cognitive process as a manipulation or transformation of symbolic representations. For example, what is to the left of circle and square? Well, you can do this. You would say it's circle, and you can do this as a manipulation of representations of the complex object and the representation of the constituents. And the motivation for this is the systematicity of inference property. You can talk about, if you can answer questions like what is the left of circle and square, you can answer a whole bunch of related questions like what is the left of triangle and diamond, or triangle and circle, and so on and so forth. Again, it's this notion of cluster of cognitive abilities that's come together, not just arbitrarily distributed. Now, corresponding category theory notion, this is natural transformation. The principle here, again, getting back to this notion of commutative square, a particular example of this is transforming composites to constituents, a composition of A and B to one of its constituents, A, and the motivation, generality or naturality of the situation. And here we saw the familiar diagram of category, functor, and natural transformation that I showed at the beginning. And the natural transformation, what it is actually just, I've shown it as a square, but algebraically what it is it's a family of these morphisms. So for every, to spell this out a bit, well, there are several ways to describe this, but one way is to note that for every, in your category here, C, for every object A, we associate an arrow, component arrow called eta A. So B is associated with an object, an arrow. And for every morphism, arrow F in the original category, so here is our category C, base category. And for every image, F image here, F image here, and every G image, there is a correspondence here. Okay. And that correspondence is given by the commutative square. So our natural transformation, eta, is actually a family of these arrows. A, eta B, and so on, such that they satisfy this commutativity condition, or this, let's call this naturality condition, going from here to here to here, to here to here. And that's the basic definition of natural transformation. And again, you can see the re-emergence of the commutative square yet again. So here's a couple of examples. Very simple example, the ceiling function. Ceiling function is a very basic function which just sends each real number to the smallest integer, not less than itself. So for example, maybe I should give an example, but for example, if I have the number, the ceiling of the number 2 point, it's just 3. Very simple. Closely related to rounding, but it's not rounding to the nearest number, it's rounding to the next highest. If it was 2, for example, then the ceiling of 2 is just 2. And we can express this as a natural transformation. How to do that is to note that the numbers, the real numbers, form a category, ordered with the usual order, form a category, in order to send as a category. Now we can send this, what's called the identity functor, which is analogous to the identity function. So it just takes a copy of this and puts it into a common category. So here we're talking about the category of reals. Here. And here, we're actually also talking about the category of reals, but we've got to do something a bit tricky. There is a ceiling functor which sends the reals to each real number to its ceiling. By x goes to this thing here, like 2 goes to 2, 2 by 1 goes to 3, and so forth. But this is in the category of integers. It's a different category. Notice for a natural transformation, the two functors must have the same domain and must have the same codomain category. So to do that, to get around this issue, we can use the injection functor to take this number here, which is now an integer, and inject it into the reals. So this is actually 2 steps here. So what we're doing is we're going to the integers, and then we're going to the reals by injection. Injection is doing it. And what we get here is a natural transformation. So here's the image of one functor, here's the image of the composition functor. And they satisfy this commutativity relationship, i.e. X, the ceiling of X must be greater than or equal to X. And the ceiling, if Y is greater than or equal to X, then the ceiling of Y must also be greater than X. Satisfies the commutative relationship. And so there we have a very similar demand. A re-representation. So you can think of this as a re-representation. So instead of looking at the original numbers, the raw data, we're looking at an approximation of this data. Maybe we don't need all the decimal points. Maybe we only need the integer value. And that's what natural transformation is doing, the re-representation of that data. One way of thinking about it. Here's another example. In this case, it's related to this notion of composites and constituents introduced before. In this situation, we have 2 functors. One is called the product functor, which takes pairs of objects and produces their product. In general, this product situation can be quite general, and there are different products for different categories. Now, if we're working in the category of sets, this is just a Cartesian product, i.e. the set of all pairs of items selected. The first item is selected from set A, and the second item is selected from set B. Now, the projection is just projects out the first object, this pair of objects. So if I project on this pair of A, B, I just get that. Now, these 2 functors are themselves related by a projection natural transformation. So we've got projections at 2 levels here. One is a functor, and one is a natural transformation. So the functor, or 2-functor product functor, is sending. The product functor is sending this to this. And the projection functor is sending the same thing, but it's sending it to this thing here. And the two things are related by this natural transformation projection. So again, you can think of this a re-representation here where we're taking holes. Thing here is holes, WHOLE, and projecting and extracting their parts. And that's with projection. Now, there's another way of doing it, and there's another closely related one, what's called this dual version of this, it's called injection, where the natural transformation is between the projection and called the co-product. And the point that, actually I'll erase some of this. Notice the correspondence here between this situation, natural transformation, and this situation. Pair that with A and B implies A. It's a logical relationship. So the conjunction of A and B implies it. If A and B is true, then A is true. In fact, this is a formal analogy as well, not just a conceptual analogy. Now compare this with another situation, or a dual situation. if A is true, implies that either A or B is true. Okay, this is a disjunctive situation. This is also corresponds to a natural transformation. But in this case, we're working with the coproduct, sum of these two objects. Now, if we're working in sets, the coproduct is just a disjunctive injection. This is also a natural transformation. This introduces another concept in category theory, the concept of duality, and these two concepts are dual with each other. A kind of reversal of the arrows, which we'll see in later slides. Maybe not today, maybe next week, not tomorrow. Okay, now I think we're almost at the end of the talk, today's talk, with two more slides, I think. Remember in the introduction, I said that there are special cases of these squares called commutative triangles. Well, the natural transformation has a special case that I'll discuss here in a bit more detail, where one of the functors is a constant functor. So what's happening here is that all the objects are being mapped to just one object. All the morphisms are just being mapped to the only relevant morphism, the identity. It's the only one that can map to. And then we have another functor G here. Now this situation can also be a natural transformation. And if we have this situation, we can simplify the diagram to a commutative triangle like this. And that's because we know that every object must be associated with an identity arrow, identity morphism, which is sitting right here. So it's not necessary to 1x. It's not necessary to express it as two separate complete arrow like this. This is simplified here. And this is just a simplification. This is different from the situation I showed you before where the arrows are being treated as objects. This is just a sort of syntactic or diagrammatic simplification. Because the identity arrow is implied by the theory, in every category, every object must have an identity arrow. We don't need to show it. Now, once we do this, the same rule applies. Going from here to here to here is the same as going from here to here. And so we call this a commutative triangle. That's a special case of a commutative square. Now, once we do that, we are very close to the end of today's talk, and we're very close to the notion of the universal morphism, but not quite. But nonetheless, here's an example of where a natural transformation involves a commutative triangle as a special case of a commutative square. Consider the number 0 in the set of natural numbers. 0 is called the least natural number. And this relationship can be expressed as a natural transformation between functors. The two functors are the 0 functor and the identity functor. What the 0 functor does is take it's a constant functor, takes every natural number and sends it to the number 0. What the identity functor does, as you saw briefly before, is simply just a copy of the original category. That's directly analogous to the identity function. Just takes objects and arrows, all the objects and arrows to themselves. I just haven't drawn in the arrows here. Now, how this works as a natural transformation, well, you can express it here. 0 is less than or equal to 1 on n. And compare that with the more traditional way of expressing it. 0 is less than or equal to x for all x in the set of natural numbers. And as a natural transformation, it would look like this. So the constant functor sends everything to 0. The identity functor sends all the natural numbers. So what you have, we might have here, category here. Let's take n as our category of natural numbers with the usual order. The constant functor is just sending everything to 0. The identity functor is just reinstating the original category here. And then the natural transformation is just the lesser than relationship, less than or equal to relationship. It just comes out as a triangle. Okay, and that's it. That covers categories, this natural transformations, and with the recurring theme of this naturality, this commutative square, or in the special case of this commutative triangle. And that is what I wanted to cover today.
Thank you. Thank you very much, Steve. And is there any question for the audience? Maybe I have just one question. For the last one,
Yep.
I kind of understand this, but so does this mean that the zero emerges as the natural least element in this kind of thinking? Or if we replace, let's say, this zero with 1, what happens?
It wouldn't work in this case. Assuming that zero is a natural number, if you were to send, okay.
Okay. So because this one already includes 0.
Yeah.
Okay.
One would sit here. The problem is that 0 doesn't fit with this scheme.
Yeah. Yeah.
This relationship here
Yeah.
is not satisfied. Doesn't satisfy the naturality condition.
So in the case of the set of natural numbers excluding 0, then 1 works,
Become
right?
the least element, yeah.
Yeah. Okay. But this formulation just picks up the least numbers of the set.
Yeah.
Okay.
And this is the general situation for the least element in a ordered set. So you can advise this too. What's called any sort of ordered set, then the least element is represented by what's called the bottom element. And it will be less than or equal to. Now not every ordered set has a least element, and I should point that out. But if it does have an element, a least element, then that's the natural transformation.
Okay. And the other thing that I also wanted to ask was that I kind of understand that, but the reason why you did that replacement with x in the last slide is to do this kind of factorization, right? Like some kind of element that always go through this one, yeah.
Yeah, that's leading up to, yeah. So what you see, yeah, good point. What you see is that in this particular situation, everything, or what we will see in the case of the universal morphism is that every element, every B here, from here to here, goes through this thing here.
Yeah, initially it wasn't
common structure.
Yeah.
For all of these structures.
It wasn't clear why you want to insert something like this, which doesn't look like useful.
No, the point about this is just to show that this situation here is just a special case of a commutative square situation. So the commutative square is really the sort of common thread of all of these definitions and examples. So you can just think of this situation as a special case of this situation is a special case of it. The reason for all of that is go back to the beginning. Where is it? Okay. This will all lead up to the universal morphism idea. Yeah, all of these things are special cases of this, or variations on this situation here. So there are various ways of thinking about this square and how you do it. So a lot of the you might wonder why, when you look at category theory from an algebraic perspective, there are a lot of definitions and a lot of constructions, and they all seem to come out of nowhere. But really, you can link them as different perspectives on this square of relationships. For example, the universal morphism. Sorry, the natural transformation. You can think of it as a sliding of this left edge across to the right-hand vertical edge. Now, the universal construction, if you rotate this, you can think of it analogously as a sliding of the top edge down to the bottom edge. And these triangles are actually really special cases of this situation. So universal morphism is a special case of this situation, an important case of this situation where there is this edge here be common to all edges. So what will happen is you can see this as a special case of what's called an initial object. It's sort of starting point. All of the arrows in this category.
I see.
Yeah. And also the notion of recursion, catamorphism, anamorphism, these sort of mysterious symbols here also speak to the same issue. Once you've got the square here, you can look at the square from different points of view. For example, you can look at it as a sliding from here to here. You can also look at it as a coherence map from here down to here, down to here. But in the catamorphism, anamorphism situation, what you're really doing is looking at as another kind of coherence relationship going from here to here to here. Or reverse direction, from here to here, back to here. So
I see. So I see now after several years I started to kind of understand, but that's why you guys always talk about the natural transformation as the most basic and important thing. And then what you're trying to say through this today's tutorial is that the variation of this natural transformation explains both universal constructions and also this catamorphism and anamorphism.
Yeah, the common link between all these.
I see.
Another, for example, the simple arrow itself, you can think of as a square where, so if these two are identities, then you can collapse these two situations as a trivial square. So this is just your square.
I see.
Your arrow is just a trivial square, and likewise, a point can be trivial.
I see.
The identity arrow. The reason for that also gets back to, and since Ross is here, Ross might be interested in it. This all gets back to this notion of relational complexity as well. So here we have what's called trivial variation. The identity doesn't do very much in terms of variation. And that's why you can think of, even though we can draw it as a square, there's only one non-trivial dimension here. Where here, if this is some other morphism, 2 dimensions, 2 non-trivial dimensions. So you think it's 2D. Another way of thinking about this is in terms of matrices. A matrix, as you know, is like a table of values. Think of a vector as a special case, as a one-dimensional matrix. Okay, so there's relationship between every vector is equivalently, any n-dimensional vector is equivalently, let's say, n by 1 matrix. So it's this equivalence relationship. between the different levels of analysis. So a vector is not a matrix in its own right, but it's equivalent to a matrix. And so the same sort of situation here. There's this equivalence relationship, but not. And category theory keeps these two things together. So again, getting back to Ross's earlier point, what makes category theory very interesting and not collapse into sort of a circularity is that it gives you the equivalence relationship, but maintains its identity. The vector is still distinguished from any kind of matrix, but it's equivalent to a special kind of matrix. Common practice in computer science too, of course. It's a way of giving.
Yeah. To me, today it was quite good that because universal morphism and so limit, colimit, and so catamorphism, anamorphism, those kind of different concepts to me, which wasn't really coherently connected to each other, was now I can consider that as a sort of the variant or sort of the part of the natural morphism. Then and how I actually change the parts of this direction, like this to that into something like reversal to here that corresponds to recursion and so on. Now, and also collapsing these two things into one point corresponds to universal morphism and so on in the tomorrow, right? Yeah, and the colimit limit. That's as well. Yeah, that to me actually makes a lot of sense. Thank you. Ross, do you want to say something?
Oh, I was just going to say, Steve, thanks for that. It's been very helpful. That last section where you've been talking about, the scribbles on the current slide there. And I think just looking at this from a sort of a pedagogical perspective, I mean, I don't know to what extent my personal difficulties in understanding this are completely idiosyncratic or whether they actually represent, some way of thinking that's more common. But I think that kind of introduction would have been quite helpful to me earlier on in understanding things. I mean, essentially, it's explaining what is the essence of category theory? Why do we care? I'm going to now split a whole bunch of hairs here, and this is why this splitting of these hairs actually is relevant to something that you might care about. And I just sort of, the way that sort of being on the receiving end of this as instruction feels to me is, I sort of read mathematical things, and the mathematical things say, hey, assume X and assume Y. And I immediately go into, why the hell would I assume X? And I can't get beyond, but that's crazy. Why would you do that? What it feels like is, you say to a mathematician, okay, we're going to build a house. Assume that the roof is floating in the air. There are no walls or anything to hold it up, but the roof is floating in the air. And the mathematicians say, fine, I'll go with that. And me, I say, why is that not falling down? And unfortunately, it feels to me like for me to understand something, I need to understand everything simultaneously to sort of form it into some sort of a coherent whole. And with the way these things are usually presented, it's sort of piecewise, but it doesn't seem to me to be sort of from the ground up so that I can rest on what's known already. It's I don't know whether that is any help in sort of production of tutorial stuff, but I imagine there would have to be at least some people who think similarly about this to the way I do. So basically starting from fuzzy and central and sort of working out, here's distinctions I'm going to make and here's why they're important, might actually be a useful way to present it.
Yeah, sure.
Yeah, that's great. Hayato, do you want to say something from a mathematical point of view, or are you there?
Yeah, but I'm on the Shinkansen. So
okay.
Just thank you for the wonderful lecture. And what Steve said is what I want to point it out.
Oh,
So nothing to say for today.
okay, great. All right. Thank you, Steve, and let's see tomorrow.
Okay, great.
Yeah.
Thanks, Steve.
Thank you very much.
Okay.
Cheers.
Bye bye.
Cheers.
Bye.
Bye.